In this problem, we're asked to find V0 of t for t greater than 0. We have a circuit with a set of mutually coupled inductors. We're going to utilize problem-solving strategy entitled S-domain circuits, as well as the one entitled magnetically coupled inductors. So if we look at our problem-solving strategy for S-domain circuits, it says, step 1, solve for the initial conditions in the circuit. So let's draw the circuit for t equals 0 minus. We will assume that we're in steady state, so we can replace the inductors with short circuits. So you can see what we've done with the inductors. And for instance, if we calculate I1 of 0 minus, which is I1 of 0, which is I1 of 0 plus, that's 10 over 10, which is equal to 1 amp. Now, for this part of the circuit, let's take and combine these two resistors in parallel. A 6 ohm and a 12 ohm in parallel gives us a 4 ohm, so the right hand side can be reduced to the following. And if we calculate the current leaving that source, it's 1.5 amps in that direction. Now, we can apply current division at this node. Notice that there's 1.5 amps entered, and it's going to split here and here, so I20 is going to be the negative of this current. So I2 of 0 minus is minus 1.5 times 12 over 6 plus 12, which is minus 1 amp. That's I2 of 0 and also I2 of 0 plus. So remember, continuity of current for the inductor. So now we've solved for the initial conditions in our two coils. Next step in our strategy says draw the S-domain circuit. So here's our S-domain circuit. Here are the initial conditions. The one on this side is L1 I10 plus M I20. The one over here is L2 I20 plus M I0. So let's calculate those. So L1 I10 plus M I20. So we have 2 times 1 plus 1 times minus 1. That gives us plus 1 volt. So then this source is plus 1. And then L2 I20 plus M I10 is 2 times minus 1 plus 1 times 1 is minus 1. So then this source has a value of minus 1. So now there's the S-domain circuit. We've calculated all the quantities for the initial conditions. And now we're ready to do step 3, where we're going to do our analysis. And if we remember back to our problem-solving strategy for magnetically coupled inductors, it says assign mesh currents. So we're going to assign two mesh currents, I1 and I2, and apply KVL to the meshes to write the equations. So let's start with the mesh on the left. We'll have 10 over S is equal to 10 I1, drop across here. Next we have this source, we have minus 1. Now, when we get to a coupled inductor, we have two voltage terms here. One is a term that we have just because we have current I1 flowing. It has a polarity like this, and it is 2S I1 of S. Okay? So we have that term whether we have coupling or not. Now, back to our problem-solving strategy for the magnetically coupled inductors. When a current enters a dot, it induces a voltage positive at the other dot. So I2 enters this dot, it's going to produce a voltage plus to minus over in the other coil. And if we look, then that has the same polarity, so it's going to be S, I2 of S for that term. So here, this term here in black is 2S I1. That's due to current I1 flowing. We have that term, whether we have coupled or not. Then the blue one here, I2 enters the dot. It induces a voltage positive at the other dot. That has the same polarity. So if we rearrange this, we can write it as 2S plus 10 I1 plus S times I2 is equal to 10 over S plus 1. Okay. So here's one of our equations. Now we need to apply KVL to the other mesh to be able to get our second equation. So if we start here and go around clockwise, we'll have minus a minus 1 plus 6 I2 plus 12 I2 plus, okay, again we have two terms for the inductor here. One is due to current I2 flow, and it has a polarity like this, which is 2S I2 of S. Now, we would have that term even if we didn't have any coupling. Now, current I1 enters this dot. It induces a voltage positive at the other dot with that polarity. And note that that's the same polarity as this term. So we have a term that's S, I1 of S, equal to 0. And if we rearrange, we'll have S, I1 plus 2S plus 18 times I2 is equal to minus 1. So here's our second equation. Now we need to solve these two equations. And what we'll do is, let's solve this equation for I1. So I1 of S becomes minus 2S plus 18 over S times I2 of S minus 1 over S. And now let's substitute into 1. So now we're basically going to eliminate I1. Now, if we look at our circuit, we only need I2 because V0, if we notice, V0 is 12 I2 of S. Okay. So we know that V0 is 12 I2 of S. So now we're going to substitute into this equation. So we have 2S plus 10. Now we have minus 2S plus 18 over S times I2 of S minus 1 plus S I2 of S is equal to 10 over S plus 1. So now we perform the substitution, solving for I2. We have minus 3S plus 20 over 3S squared plus 56S plus 180. Now let's factor a 3 out of the numerator and denominator. So we have minus 3 times S plus 6.667 over 3 times S squared plus 18.667S plus 60. And of course, we can cancel the 3's. And if we remember that V0 of S is 12 times I2, And then we can write V0 of S is minus 12 times S plus 6.667 over S squared plus 18.667S plus 60. So now there's our ratio of polynomials in S that we need to conclude step 3 of our problem solving strategy. Now for step 4, we're going to perform the inverse transform. And we have V0 is minus 12 times S plus 6.667 over S squared plus 18.667S plus 60. Now we need to find the roots of our denominator. So we have S is equal to minus 18.667 plus or minus the square root of 18.667 squared minus 4 times 1 times 60 over 2. So we have S is minus 18.667 plus or minus 10.4137 over 2, and that gives us S is minus 4.1267 and minus 14.54. So we have two distinct roots this time. We don't have any complex conjugate roots. So continuing on with our inverse transform, we have V0 minus 12 times S plus 6.667 over S plus 4.1267 S plus 14.54. And our partial fraction expansion then is K1 over S plus 4.1267 plus K2 over S plus 14.54. Now solving for K1, we multiply through by this term, and then let S equal minus 4.1267. That gets us minus 2.9274. And then K2, we multiply through by this term now, and we let S equal minus 14.54. That's minus 9.0726. So now we've completed the partial fraction expansion. So V0 then, V0 of S is minus 2.9274 over S plus 4.1267 plus minus 9.0726 over S plus 14.54. So V0 of T then, minus 2.9274 e to the minus 4.1267 T minus 9.0726 e to the minus 14.54 T U of T volts.